right? We make an alcohol there, but now we have, instead of one hydrogen there, we have two.
What's the purpose of the acetone?
Ah, good question there. What is the purpose of the acetone? What is it acting as here? It's a solvent. And acetone is what kind of solvent?
Aprotic.
Aprotic?
Aprotic solvent. So we're going to be favoring that sweet SN2 reaction. We're actually going to speed it up using a nice aprotic solvent.
So what's so important about the SCH3?
So the question there was, what is so important about this SCH3? What is SCH3 acting as in this reaction? What is it?
Base?
Nucleophile.
It's acting as our base, our nucleophile, right. This guy is what's going to take the place of bromine.
Oh, okay.
Gotta be accurate. There you go. Gotta attack backside and kick bromine out of here. And that's how we get that stereochemistry inversion.
Why are there two hydrogens on the bottom of the final product?
Ah, good question. So how do we go from having one hydrogen here to having two in our product? Where did the second one come from?
From that
The
hydride.
hydride.
Yep, from the NaBH4. NaBH4 donates some nice H minuses to solution that will attack our carbonyl just like Grignard's will. So when we attack it, we get a hydrogen that attaches there instead of a carbon chain. And we still get an alcohol at the end when we add that nice methanol as our proton donor.
Do we have to draw two H's or if we don't draw it, we do?
Yep, we're all chemists. Do we have to draw the hydrogens there?
No.
Nope, we don't have to. We could literally leave this guy bare without the hydrogens being there, and our answer's still valid. In fact, on the answer key, he doesn't even draw the hydrogens there. I just put them there so you guys can see that they're both there. Any other questions on that one? Anything else? Anything on this page so far? Ah! We know what this is.
SN1.
That's double SN1. Get these guys out of here and put some halogens on there. If this song was about single ladies, you would not put a ring, you'd put a halogen on it. That's all this is. Yep. All the tertiary carbons. You're welcome for having that stuck in your head. But all right, what about the chair? This looks menacing, right? It looks like it looks ugly. Has no soul.
Strong base.
But yeah, we got ourselves a nice strong base down there. We have a leaving group. What kind of reaction are we doing here?
E2. Tertiary carbon.
We're doing some of that sweet E2.
This is the one where if it's a tertiary carbon, it would prefer the E2 because of the base.
Ah, good point there. So now normally when we carry out the E2 mechanism, this carbon would be tertiary, and we need a strong base to do it there. But what kind of carbon is that we're sitting on? It's a secondary, so here anything is up for grabs. So now it's going to come down to our nucleophile, which also is our solvent. So it's a strong base. It's also aprotic. Both of these are going to favor the E2 mechanism over SN2. Now we will get a trace amount of SN2 product, don't get me wrong, but that's why I want you to draw the major product, because there is a minor product of SN2 that happens. That OCH3 will attach a little bit there, but it's by far going to favor the E2 mechanism due to these two constraints. So we can put our double bond either here or over here. But now, do you guys want to see how to turn these into bond line? All right. So what kind of backbone is this? What kind of general structure we draw first?
Hexagon.
Cyclic.
We should draw a hexagon, right? These are cyclic hexanes. And we can have two products, so we just draw them out this way. Now I'm going to assume that the bromine, the carbon that the bromine was attached to, is up top. So I'm going to put my little dot right there. Now I could have one on my right-hand side, so over here or over here, right? I can put a bond here or here. And now we need to start assigning some planes to the other molecules that we have. So one carbon over carbon. We have a methyl here, right?
Yes.
Is he wedged or dashed? What is he?
Dash.
This guy is going to be dashed. And how do we know he's dashed? Because the hydrogen's pointing straight up into the air. That is your giveaway there. So that methyl is going to be dashed. Is it different over here?
No.
Nope. Same thing. And then we move over. What orientation is this methyl in? He's wedged. Hydrogen's dashed here. And it's the same for both. And then another carbon over. What orientation is he in? Dashed or wedged? Yep, he dashed. He dashed though. Yeah, they're both going to be dashed. And now we've drawn the products, but have we answered the question fully yet?
No.
No. What are we still missing? That relationship. Is it complicated?
No.
You cannot go through life without an updated relationship status on Facebook. You must circle one of the two options. So, is it a single isomer or racemic?
Racemic.
It's racemic. It's the only option we get that makes sense. Any other questions on page 2? The bromine up here? It's like, question 1. Out here tonight. Goodness gracious. I was not expecting this many people to turn out on a session that, like I said, I announced the day before. But okay, like I said, today's session we're going to try to hit a lot of the problem children in the practice midterm. Because a lot of these questions are probably not going to change. I don't even know which ones because Wagner hasn't even made the exam yet. So I couldn't even tell you which ones are going to change. But a lot of the concepts are going to be identical. And we're going to start off with problem child number 1. The one that everybody hates because you have to think extremely hard about this one. And it's the retrosynthesis problem. Or, on this particular midterm, it's question 9. So if you guys want to flip there now, I'm going to try to break this one down so you guys won't be so terrified of it. Now, I'm not going to show you how to do this via retrosynthesis because, 1, you don't even get credit for doing the retrosynthetic pathway. If you draw just that, you get 0 points for this. And out of 32, you do not want to get 0 for this. And also, retrosynthesis takes time. Going backwards and then having to redraw it forwards, basically you're answering the question twice. So I'm going to show you how to approach this from the forward direction only, because that's the reaction direction you're going to get credit for. So let's take a look at this guy. All right, well. So we've got to show how we can make this guy that's in this box. You will be given this. You have to show how we make this product given these 2 starting materials. And we're allowed to use any reagents we can come up with. We can use PCC, we can use methanol, we can use product solvents, we can use whatever solvent we want. But we have to use these 2 starting materials. Now I'm going to tell you guys right now, the one big thing we need to be looking for is, how did this guy change? Because you can notice the backbone of this final product is this guy. We just made some slight modifications to it. So what do you guys notice is different between menthol and this guy? What do you guys notice between the 2?
Double bond.
Yeah, right. We have a double bond that's sitting in here now. What else do we have that's new?
Methyl group.
In the back.
Right. We got a methyl group here, and we don't have the alcohol anymore. And you also noted that, well, we put a double bond here. That also removed our stereocenter, so this is no longer wedged. So we somehow attached a methyl group there, and we also added a double bond somewhere along the way. The big thing that's going to be the dead giveaway here is going to be this right here. That bromine's sitting right there. Now, as a rule of thumb, for the most part, when you see bromine sitting on one of your starting materials, there is one type of reagent you should be thinking of. Can you tell me what it is?
Grignard.
Grignard. Yep. This guy right here is telling you that you're going to be using a Grignard. And not only because of the bromine, but also because we had a methyl attached here, correct? There's a methyl sitting on that bromine. So somewhere along the way, that methyl group attached to that carbon somehow. And Grignards are one of the easiest molecules we know that allow us to make those brand new carbon-carbon bonds, because whatever the Grignard is attached to attaches to your carbonyl group. But that's going to be our very first step. The first thing we have to do. We have to make a Grignard out of this. So how can we do that? We take methyl bromide, and then what can we add to this? Come on, you guys know how to make a Grignard. What are we throwing in here with
Magnesium.
this? Yeah, magnesium. And yes, you can literally just put magnesium over the reaction arrow. You can toss in magnesium. And we make our nice little methyl magnesium bromide Grignard. So I'll just put a little 1 here because that's technically going to be our first step, is creating the Grignard that we're going to use later on. But okay, we made ourselves a Grignard. Okay, so now it has to attack something, right? Do we have anything on here that this Grignard can attack yet? Good point there. Now, we have an alcohol sitting here, but now when we use a Grignard, our final product is an alcohol.
So
What do we need for a Grignard to attack? There's 2 choices we have.
Ketone or aldehyde.
Ketone or aldehyde, that's exactly right. So ketone or aldehyde. So if our methyl attached right here, that means this molecule at one point had to be a what? It had to be a ketone, right? We have 2 carbon chains going off this way. So we have to somehow make this whole section right here somehow carbon double bonded to oxygen. Now, we know a molecule that can do just that. What is it?
PCC.
Sulfuric acid will get rid of the alcohol, but we don't want to quite get rid of that oxygen.
Oxidate.
PCC.
It's an
Oxidate it.
abbreviation.
PCC.
PCC, right. PCC will allow us to turn that alcohol into a carbonyl group. Now, a lot of you guys probably haven't seen a whole lot of reactions with PCC in it. You just know, okay, it makes a double bond somewhere. But there's something special that PCC needs to have. First off, who can tell me what PCC stands for? It's okay. Nobody knows and nobody cares. But it's pyridinium. Make sure I spell this correctly. Chlorochromate. That's PCC's full name. Now, this is going to be very, very important to know. Not necessarily the name, but the general structure for PCC. The actual portion of the molecule that actually does something useful is this piece of it. It's the chlorochromate part that actually does the actual portion of the reaction we care about. It's this part. And that's going to be huge for a question that comes up later, because you're going to be given a molecule that looks a lot like PCC. But you guys aren't going to know that unless you know what PCC actually looks like. And now, if I'm going to be accurate with PCC, I have to draw the other half of it, which is the pyridinium part, which is this stupid thing that I hate with a passion. We use this to freaking stabilize it in solution. That's where the pyridinium part comes from. But again, it's this guy that's going to be the big player in this whole mess. It's basically chromium with 3 oxygens and a chlorine hanging off of it. Now the chlorine doesn't actually do anything either, it just kind of chills there. But now PCC requires a specific set of conditions in order to work. So now there's 2 conditions we need to have for PCC to work. Well, what do you guys think one of them is? That's right.